Part 3 of Unit 10 is about integrated rate laws. Alright, there's actually two types of rate laws. Differential rate laws show the relationship between concentration of reactants and rate. That's what we looked at in video 10.2, and those are just usually referred to as rate laws. Integrated rate laws show the relationship between concentration of reactants and time. To determine the reaction order for an integrated rate law, we're going to have to graph some data and look at the graphs and try to find a graph that results in a straight line. If we graph time versus concentration and it's linear, then the reaction is zero order. If we graph time versus the natural log of concentration and it's linear, the reaction is first order. And if time versus 1 over concentration, or the inverse of concentration, is linear, the reaction is second order. You need to remember these simple rules for determining the order of an integrated rate law. And unfortunately, we don't have simple, easy equations to remember for integrated rate laws. The rate law equation for a zero order reaction is concentration of reactant A at time t minus the concentration of reactant A initially, that's a minus sign, is equal to the negative rate constant times time. And the units for a zero order rate law are going to be molarity per second, which is the same thing as moles over liters times seconds. For a first order reaction, the equation is natural log of reactant A at time t minus the natural log of the initial concentration of reactant A is equal to negative k times time. The units for a first order integrated rate law are going to be 1 over seconds. And for second order, the equation is 1 over the concentration of reactant A at time t minus 1 over the initial concentration of reactant A is equal to positive kT. And the units for a second order integrated rate law are going to be liters per mole times seconds, which is the same thing as 1 over molarity times seconds. Lucky for you, the first order and second order equations are given on the AP equation sheet, so that means they're also on your green sheet. The zero order equation, however, is not given. Only the first and second order equations are. So to solve an integrated rate law problem, it'll look something like this. For the following data regarding hydrogen peroxide decomposing into water and oxygen gas, determine the correct form of the integrated rate law and determine the value of the rate constant. So we've got a decomposition reaction. H2O2 is breaking down into water and O2, and they show us the concentration of our one reactant decreasing as time goes on. We would need to graph this data in three ways: time versus concentration, time versus the natural log of concentration, and time versus the inverse of concentration to identify the reaction order. If you have a graphing calculator, I will show you how to plug this data in and graph it in class. I've gone ahead and made these three graphs. So this is time versus concentration. This is time versus the natural log of concentration. And this is time versus the inverse of concentration. Obviously, since time versus the natural log of concentration is linear, the reaction is first order. So we can solve for this rate constant by solving the first order rate equation for k, or we can determine the slope of that straight line. Either way works. I'm going to go ahead and plug values in to the first order integrated rate law and solve for the rate constant. I'm just going to choose the data that was at time 1800. So my equation, again, it's first order, so it's going to be natural log of H2O2 at time t minus the initial concentration of H2O2 is equal to negative kt. So I'm going to use time 1800. So at 1800 seconds, the concentration of H2O2 was 0.22 molar. So natural log of 0.22 minus the initial concentration, natural log, that was supposed to be an ln, whatever, ln of 1 is going to equal negative k times 1800, because that's how many seconds had gone by. So I'm going to simplify this side, natural log both of these, and subtract. I end up with negative 1.51 is equal to negative 1800k. I just moved things around on this side. So now to solve for k, I just have to divide this by negative 1800. So my rate constant is going to be 8.39 times 10 to the negative 4th, and it's a first order integrated rate law, so my units are 1/seconds. This table gives a nice summary of all of the integrated rate law information, and actually includes differential rate laws as well. Shows what the two types of rate laws look like for 0, first, and second orders. These are the same equations I showed you, they're just rearranged. The way I showed them to you is how they appear on the AP equation sheet. It reminds you of the graph that produces a straight line, the relationship of the rate constant to slope of that straight line, and the half-life equation. We can use these equations to figure out how much time it takes for half of that initial concentration to go away. It's not a bad idea to copy this table down. Graphical analysis of the following data determined that time versus 1/concentration, or the inverse of concentration, produced a linear graph. Use the correct integrated rate law to determine the value of the rate constant, including units.